And so I get 1 over q plus p squared minus 1 over q plus p plus lambda squared. Okay. And this, actually, these two terms are separately integrable. Okay. So here, let's do the first one. You get a 1 over p by doing that integral. And here you get a 1 over p plus lambda by doing that integral. Or I could calculate it the other way, because I've been so strong that I've done this loop integral already explicitly. And this is equal to, well, if I had kept the p there, this would be 1 over p plus minus 1 over p plus lambda. Okay? So you can check it. The sanity check is passed. But for lambda much bigger than p, p is my external momentum. Okay? I determine it by some process that I'm interested in. It's worth remembering that in the middle of some Feynman diagram, where these one-loop blobs are connected. Some connected diagram is actually made out of these one-loop blobs. But these are the true external momenta, okay? P1, P2. But even if I just look at this one pi piece of it, this line is going to be P1 plus P2. So the sub-analysis I'm doing at the level of 1 pi vertices, the momenta that are coming into this 1 pi blob are always linear combination of the true external momenta of your process, whatever that happens to be, maybe in the process of calculating an S matrix. So truly, these are the p's that you're seeing on the outsides of these gammas are truly linear combinations because of this tree-like structure. They are truly linear combinations of the experimental momenta. And the cutoff is meant to be some physics, representing some physics, much, much heavier than the experimental momentum. And you can see that then this just looks like this. Which of these two is the dominant gut? Obviously, this one, because this one is going like 1 over lambda. Okay? So, now you see all the bits. Okay? You see that the derivative becomes something where you can do the integral. Even if you threw away this term, you could still do the integral, and you'd get something fun. Does that answer sort of the spirit of it? You can play, you can actually do this exercise here too.
Now we integrated that, and we got the polynomial.
Oh yeah, great. Sorry, I forgot. Yes. So suppose if I integrate. Then, if I integrate I of p lambda, then I get I of p. Sorry, if I integrate dp of this, then I get ip is equal to log lambda plus p over p, but plus an integration constant. But that's not the full thing that I want to point to. Of course, if I wrote this, then this particular k is 0, really. But I wouldn't know if all I'm calculating is the derivative. I wouldn't know whether this is 0 or not. But in fact, I want to think about another thing. Let's integrate the approximate derivative of I lambda. Well, the whole thing about saying the word ultraviolet insensitive is taking the cutoff to be infinite is approximately the same as taking the cutoff to be large. Okay? So let's calculate the integral of this approximate, or if you like, the UV limit of the cutoff, since I can take it for the derivative that exists. And of course, this is just one word. Then what it says is that get an approximate I of p. Now, which I of p are you going to get by doing it? You might say, oh, I'm going to get I of infinity of p. Heck no, that doesn't exist. We know it doesn't exist. It's divergent. This would be a nonsensical statement. Nobody has told us this exists. That's why I use the word approximate. I know for sure that the integral of this with some choice of integration constant is I of lambda of p. I know for sure that's true. I also know for sure that whether under the derivative sign, whether I put lambda or infinity, it's a good approximation. So therefore, I know that the integral of this good approximation of this is this, up to an integration constant. So what it gives me is log 1 over p plus k. Okay? I just do the integral of, so the integral of that is log p and then plus k. Okay. This k, nothing stops me from writing it as log capital K minus log capital. In which case, the whole thing combines into log of p over k, which is only a sign mistake different from what I wrote here, but that's because I screwed up. But now you see what you lost. What you lost by differentiating, taking the ultraviolet limit and integrating your answer, is you merely lost which cutoff you were thinking of. The correct answer was log lambda over p. I got log k over p. I don't know which lambda you're thinking of. But since we're trying to get the physics to not care about lambda, this is the, but if you want, this k, the information I lost, I lost that k equals lambda. I lost the information about what this polynomial is as a function of the cutoff. And we're going to see that, if you like, experiment or Gedanken experiment will provide us back that information. Okay. What exactly this polynomial is, we will just take it numerically from experiment. Because by taking only the derivatives and saying, oh, at least I can calculate those, we are losing this part. But it's a polynomial, it has some number of constants that I don't know, go fit it to experiment, and then it's done. That's the spirit of this.
So there are ln p is a unique finite, and ln k is a polynomial.
ln log p is
Your unique finite term. And log of k is your polynomial that's UV sensitive.
That's right. Log p is like it's non-analytic in p. It's finite. I can calculate it. It's a prediction. The log k is not a prediction. But look, this log p is a beautiful prediction because it's a function of p. It's a continuous infinity of predictions here. This log k is one number. Can't afford to just go measure one number? Sure you can. So that's the thing. You measure one number and you get a continuous infinity of predictions. Right, that's the spirit. Yeah.
I have two questions. One is that it seems like this k is, this is really on this UV dependent, UV sensitive part is only really a polynomial in the lambda goes to infinity limit. Because otherwise this k, I might be getting that wrong, but it's really something like lambda plus p or something. I think there's a...
So you're worried about the subdominant term here? Or
I'm not worried about it affecting anything much numerically because it is...
no, I understand, but
principle,
even vaguely conceptually,
yeah.
this is what you prefer. So let's just look at what that would have been, okay? So there's this. So correct, I was being sloppy, apparently being sloppy there, but I'm not, really. times 1 plus p over lambda. So this is equal to log of lambda over p plus log of 1 plus p over lambda. But if I expand, so here is the series expansion in the things that I had not bothered to write down over here, if you like. First of all, it is analytic. It is sort of, it's analytic in P in that sense, at least in the vicinity that I want, which is P much smaller than lambda. Okay, it looks like it's got a log this, that, and the other, but actually in this vicinity, it's analytic. Okay, so if you think of P in the complex plane, but the P is much smaller than lambda, even a log would be analytic in this vicinity. There's no branch cut or anything like that that's sort of obstructing me here. And indeed, it has a nice series expansion. And indeed, you can throw it away because, as you said, numerically, I would say, let's work, or if you want, even formally, let's work to some power in, so I want to keep all the sensitivity. These are clearly insensitive to the cutoff, but I want to keep how insensitive? Well, I don't know, let's work to 1 over lambda, p over lambda to the 17th power, okay? Well, then this will just be a polynomial. And we can either keep it there or not, but numerically, of course, it's we've chosen a large enough lambda that we don't care. When you get to effective field theory, you actually care about things like this. If lambda is not really sort of infinity, but just big, then these terms actually matter, but we're not doing that.
Okay. Because that's what I was thinking, and I was thinking that that meant that this polynomial, from the viewpoint of an effective theory, isn't really a finite polynomial. It could be in principle
Correct.
an infinite polynomial.
Correct. The way it becomes finite is you decide not only what order in perturbation theory you want to work to, like g to the 7th. You also, when you think of lambda as just being bigger than my experimental scale, but still not arbitrarily big, you also work to something in, you also work to some order. In effective field theories, you work to some order in experimental energies over new physics scale, if you think of this cutoff as being a proxy for new physics scale, right? You work to that order, and then it becomes a polynomial. And only then you get all of the value that I'm teaching you for normalized theories. And this, it's a very, very simple point, how you do effective field theory when this scale is not arbitrarily far away. It's a technically very simple point, but it was a major conceptual obstruction for a very long period of time. So much so that a large part of our community has fractured into two. Those who came once it was conceptually and calculationally easy, who grew up in the post-Carl Lagrangian of pions age, and people who missed out, for whom it always seems like this is really fake and this is wrong. Non-normalizable theories are completely useless and there's nothing to be gained from them, even though we use them and calculate real cross-sections all the time. So it's a fine point, and a certain amount of history goes into it. But in fact, I want to say that I said it exactly right, because all I said here was it's UV finite, and I said that's not what I really mean. What I really mean is it's lambda insensitive. And so the terms that we're pointing to here, whatever I've written here is meant to be modulo lambda insensitive terms. And these are. Whether I choose to expand or just look at it like this, even here, this is a lambda insensitive term because log of 1 is 0. Okay, so then I think I can show you one simple piece of magic. What is the great virtue of being polynomial? One loop consider a modified path integral, where instead of using the original action, let me just think of phi to the fourth or something, scale. Instead of using the original action in the path integral, you take whatever you were using that was giving you whatever these gammas are, and you subtract the divergence let's keep the cutoff there. In other words, you can't subtract infinite. That doesn't make any sense. But you subtract off this. This is our polynomial in disguise. Okay, if I Fourier transform back, this just becomes the gamma n, some gamma n contribution. It's the divergent piece in this gamma n. The gamma n then gets multiplied. To get gamma of phi, the gamma n gets multiplied by phi's, in which case you end up with a local action, right? For example, if this is the divergence in gamma of 3 is given by some polynomial p, which equals, say, p1, I'll just be schematic, p1 squared, p2 squared, times some function of the cutoff. If this is the divergent part of this expressed in momentum space, then in position space, it's saying that gamma 3 of phi divergent, just the divergent piece that I'm pointing to here, is the Fourier transform of this, which is equal to integral d for x. This p1 squared becomes some d squared acting on some particular phi whose momentum is p1. And then there's another d squared acting on some phi whose momentum is p2. And then there's somewhere else lurks another phi, the one whose momentum is minus p1 minus p2, but it's not got any derivatives in that sense. And with a coefficient that's as f of lambda. Okay? So this and this, we're pointing to the same object. But if somebody tells me there's a divergence like this, what I'm saying is, consider a new action, which is whatever action gave rise to this, minus this itself. Okay. And now with this modified action, let's calculate again and see if we still have divergences. Okay, that's the key. So the claim is, in this modified, with this modified action, with this modified action, UV sensitivity cancels to one loop order. So I want to phrase it in the sort of level of generality that, that we want. I want to just be very general. And that is to think of this original action. The original action, if the tree level action, I mean the action that just gives you this, the effective action, if you work to tree level, is the action. Because there are no loop level effective vertices that you can draw, because I'm telling you to work to tree level. But that doesn't mean the effective action vanishes, because there are vertices there, the tree level vertex. So if this is phi cubed, then it is a, you know, if I amputate this, this is a 1pi diagram, it's a rather simple one, but it is there. So even tree level is sitting inside gamma. So all I'm pointing to here is, this is the tree level effective action. The action and the effective action are the same at tree level. There's nothing clever about tree level. I'm putting an h bar to the 0 there to say that it's the, you can think of it as the effective action when you work to h bar to the 0, or really the leading h bar. And here I want to formally put h bar to the first power. Now everybody knows h bar is 1, and this is really a shorthand for giving the size of the various vertices in this thing relative to the size of the various vertices here. For example, here you might have some lambda phi to the 4th. And I'm just saying formally, let's say that that is order h bar to the 0. Actually, counting h bars is really counting loop counting parameters, or couplings. Okay. But then if you do something like this, and you discover something that is sitting in your one loop effective action, in the one loop approximation to the effective action, it might have some divergences. But because there's an extra h bar there, any divergence you find here will look local, but it'll have an extra power of h bar relative to its cousins from the tree level effective action. Okay. So the general way I want to write it is this, that gamma of phi is equal to a loop expansion. It's the and you know that even if h bar is 1, that this is really a code to say that a 4-point function inside here, a 4-point function inside here is going to be the loop counting parameter smaller, suppressed relative to the 4-point function here. A 4-point function here is going to be loop suppressed, it's going to be 2 loop suppressed. Remember the loop counting parameter for say phi to the 4th is lambda. So this is going to, any 2 loop Green's function here is going to be lambda squared suppressed with respect to this. But since I want to talk about theories with 5 different coupling constants, I told you how to think about it in terms of this h bar, we can just write it like this. Anything here is going to be a 2 loop factor suppressed relative to this. That's all this means. I've just broken down the effective action into however many loop orders you want to go. It's a slight twist on saying work in perturbation theory. Instead I'm saying, let's just work in loops. Equivalent. And right now we're just focusing on this. And this term here, deep theorem, it's the action that you plug into the path input. Okay? The so-called classical action is this. Okay, so that's meant to be obvious. And so here's the punchline of this, which is that when we modified action, with our new modified action, let's recalculate what the effective action is. It is given by h bar to the 0 and this S original, so S original, then if I forget about this term and I draw all possible diagrams, I'm going to get the h bar to the 1 gamma 1 loop original. But wait, I forgot about this extra action that I added. I added this term. Well, see, it's the thing you plug into the path integral for the same reasons. It's going to show up as S1 loop local divergence whose divergence? Of the new modified theory? No, just the old one. So local original divergence. How many h bars does it have? Well, this divergence already came from one loop calculations. So it's got an h bar to 1. But wait. This is taking something which is formally of size h bar and writing out at tree level that it should show up just like the tree level action. Okay? This thing is a unit, so it's of course going to happen in exactly the same way. But you might take some sort of vertex out of here. You can take in a path integral, a vertex from here can be used to make Feynman diagrams. In fact, it can be used to make loop diagrams. But if I actually use this, so if there's some vertex here, which has got some h bar in it there, if I use it to make a diagram, that's going to be another h bar from the loop. And the net effect is 2 loops. It's 2 h bars. So this is true plus h bar, plus order h bar squared. So we're doing an expansion in loops. You can take the action which is ordered h bar to the 0 and use it to form loop diagrams. In that case, the effective action will be the thing where you don't bother to make any loops, or the loop diagrams gotten by using the original action, and thereby incurring an h bar because you did a loop. Or you can take this these effective vertices here, and you can do tree-level diagrams with them, in which case, so it's formally loop-sized, but you do tree-level diagrams with them, and then it'll show up just like the tree-level effective action. It'll show up just going for the ride. But you cannot take these vertices, which are formally loop-sized, and plug them into loop diagrams, because that will be order h bar squared, which is not yet our work. Okay? But now you see that this is UV finite. Why? Because by definition, this is the loop divergence in this. If I subtract it, I'm left with something finite. The end. Okay? So by just modifying the path integral, by modifying the action, which is the weight in the path integral, but not changing it from being local, it's still a local action, I am able to get something UV finite. And it looks like you literally just suck the divergence out of the thing that was bothering you. This is sometimes therefore called subtraction. It's a terrible word because it looks like you're doing something. I don't like the divergence there, so I subtracted it. And you don't know, well, did that leave all the principles of relativistic quantum space-time intact, or have you mutilated them? That's not obvious by the word subtraction. A slightly better way to say it is this, that we modified the effective action, we modified the action in the path interval, but we modified it in a mild way, in the sense that it was already a local action, and I changed it to some other local action. And by doing that, I get something that is actually ultraviolet finite. That's a slightly better way of saying it. It still seems like you did something. Look, I did something. I could have not done this, but I did it. And so next time we're going to see that no, this is actually a very passive thing. We're not doing anything. We are noticing something. Okay? It just looks like you're doing something when you're doing the calculation, but actually the physics is not doing, it's not being changed in any way. We are merely noticing something. Okay, so we'll have to take that up next time.